Welcome to our fifth presentation. It's going to be an interesting one about 3D models and movement capturing. This will be presented by two presenters, Piotr Storożenki i Marcina Panka z firm Bones and Appsilon. A tytuł jest Machine-Made Human Motion Using ML to Generate Animations.
Thank you, and welcome to our talk about generative AI for human motion generation. I'm from the motion capture studio, and with me it's Pasza.
Hello, I'm from Appsilon.
The talk will be constructed in a way that will introduce you to the subject, what is computer animation and motion capture. Then I'll present the business part of the whole project, and then Pasza will deep dive into technical part. And in the end, we'll give you a glimpse of how we think the future of computer animation, at least human animation, will look like. So Bones is motion capture studio. This carpet in the back with these squares is a floor on which real people perform their roles, and the movement of these people is translated into 3D characters in games and movies. And we operate for 10 years now, and 3 years ago we started the idea that started the project that it's possible to automate at least some of the processes that we are doing, and there was almost none automation back then. So we invited Appsilon as a technology partner for machine learning part in that, and we got a grant from NCBF for that.
Yeah, and why Appsilon? So we are a data company. We're making data infrastructure, data visualization, data dashboard, data, all kind of data. And regarding ML, we focus on computer vision, and especially on doing research in computer vision. And this motion capture field is very, very interesting, very fascinating for us. And we decided to collaborate with Bones, as they are like industry experts in this field. And why motion capture data? Marcin, please tell us why motion capture data.
Okay, so when you create a game, for example, you've got like an hour or a few hours of in-game cutscenes to deliver, and you need to create pretty fast. So you hire a bunch of actors, you give them scripts, and you put these actors into lycra suits and put some small markers, as you can see on this picture here. Cameras all around the stage sees only these markers. So there is a threshold. They sees only these markers with infrared light. And when talking about the performance capture that is needed for the whole experience, we are talking about a bunch of stuff. The body is the main important thing, but there's also a face with a camera in front of an actor. There is a finger capture with a special gloves, because fingers are relatively small and their movement is very important. You can capture also the voice of a character as a separate channel, and you capture props, which are small items that an actor interacts with, right? Like a gun, a mug, or anything. And in this project, we focus only on the first thing, the body capture. So the system, motion capture system, sees only these markers on an actor. So they create a cloud of markers, as you can see on this in this image on top left, and Then system chooses the subset of these markers and labels markers, like giving the name for every marker, because their naming and location should be very precise to get in the next step the very precise skeleton which is aligned to these markers, and it's like inside the body of an actor. Of course, everything is totally virtual. So we've got this virtual skeleton of an actor, and movement is being processed only on this skeleton. So this skeleton is like the thing we are working on all the time, and when I'm talking about the animation, I'm talking about the movement of this skeleton. So here at the bottom you see what we are working with most of the time. So there is a skeleton inside the character, and there are these little points which are the markers on an actor in real life. We recorded 120 frames per second, so you get the movement of every piece of this skeleton, every bone, in every frame. Then we've got a skeleton, and we want our character to move. Fortunately, every 3D model has its own internal skeleton, and the task is just to translate the movement from actor to the model. And this process is called retargeting. We don't have time to dig into that, but it's like translating the movement from actor skeleton to 3D model, and basically you can translate it any way you'd like. So you can, for example, translate the movement from actor to an orc or a dwarf or any character you'd like. Okay, so what's the problem? The main problem is that it's very, very time-consuming. To create a simple animation like someone attacking with a sword or something like that, that lasts for 3-5 seconds, it takes 1 to 3 days for a very skilled 3D animator. And when you've got many characters in a game and you need to create hundreds of these kind of animations for every character, it's really time-consuming and capital-intensive. An alternative is motion capture, but it's also capital-intensive. So to perform the session, you need to hire a bunch of people. You need to hire actors, equipment, etc. Process this data. It also takes a lot of time. So the idea was to automate it in many ways, and the our first goal was to change the style of characters. Can you click? And after these 3 years, this is like our first model that changes the style of a character. So you've got a base animation that it's like a content of animation. Here is just walking. So the character walks forward, and you can choose a style in which it should be performed. So when you, for example, choose a sad style, it generates the same animation. So like the steps are mostly in the same position, but in a totally different style. As you can see, there are a lot of subtleties here, like this body position and timings, etc. And here's the guy who's.
Let me interrupt for a second. Obviously, this is not our first model, right? We trained like hundreds of them, and only after a lot of iterations we got to this point. Yeah, continue.
Totally. Yep. So this is it in a nutshell. And now I pass the microphone to Pasza to tell more
No,
Okay.
please
Yeah,
tell us
sure.
about the data set that you have.
You're right. There is one more thing. So to create a model like that, you need architecture and data. Starting with the project, we knew that there are no data sets for human animation. There were very few of them, and it was like hundreds of animations or something like that. But we knew that it's not enough, so we decided to record our own data set. That turned out to be the biggest motion capture data set in the world. Right now, it's 10 times bigger than any other right now. Can you click?
Yeah, sure.
So we tried to capture every possible movement, like everyday stuff, fighting, playing instruments, sleeping, laying, dancing. There are a lot of dances in the data set, so that the characters can perform just any movement that you can imagine.
Yeah. So this is our data set, right? And now we can do a machine learning on this data set because we have data. And as you know, in probably many of your projects, data is the problematic part, right? So you have great ideas, but you don't have enough data, right? And here we have a lot of data. So we'll go into details of how we represent this data, but just files take like 250 gigabytes of just raw text files. So it's a lot. Right. Let me go to the next slide somehow. Okay. But I thought like what might be interesting for you to hear. And I could dive into the architecture that we're using, but then it will be only interesting for me. Maybe I'll discover some errors in my thinking, and not for you. So I decided to go and speak about things that might be useful for you in your projects. And first I will tell something about modeling insights, and then about some universal ML advice. First advice is know your mathematics. And what do I mean by that? There are different data representations that you can use for different projects. Or not for different projects, but with different data. For images, we just represent image probably as a tensor of dimensions like 3, height, width. With text, it's much more trickier, but we tend to use the representation after tokenizer, where we get something that is of the length of the number of tokens in a sentence. We have all the LLMs presentations in different rooms. I'm glad that you came here. Right, with sound, I wanted to give the sound example because first, it's somehow relevant to our project, surprisingly. And then here you can easily think about different representations for the same data. So you can just have a time series. In case of a stereo file, you have like two channels, and then you have time series of the amplitude of the volume. You can have some like MFCC features. Maybe you've done some projects on Warsaw University of Technology, and then this trick gave you like 5 at the end of the semester. But you can also use FFT or something else. Okay, so how to represent the motion capture data? usually we use, first, we have some base skeleton, and the data that Marcin collected, or like his team, we are retargeting all the data on one skeleton, and then on this skeleton you can apply different rotations to different bones on different joints. These are joints, and those are bones. By the way, Bone Studio is from those bones, right? Clever.
May I? Joints were also available, but we choose not to.
Yeah, might be sketchy. Good point, good point. Bone, so we have rotations on each joint. And if you have rotation on this joint, and then on the this joint, and then on the next, you can model the whole movement, and you have rotations in different points of time, and you have the whole movement, right? So you represent the animation data as tensor j, where j is the number of joints, let's say 29 in this case, 3 as a number of rotations. We'll go into this in a second, and t is like the time. And you might wonder, how big is this skeleton? This is banana for scale. Okay, so 3 is a 3D Euler angle, and you can describe every rotation in 3D by a set of 3 numbers, and they are called Euler angles. And you can say that each rotation is described only by one set of those 3 numbers, caveats apply, and so on. But that's the standard representation that we get from bones. But we want to do machine learning on this, and the problem is that this data is non-smooth in many cases. This is just an example, but if you want to take this arrow below the x-axis, you must do the jump from 180 to minus 180. And neural networks don't like this kind of jumps, so we use a different representation. And some of you might remember that you can use quaternions, which are like 4D numbers to represent rotations. And there is this ugly and hard and, yeah, let's say hard and ugly equation to convert one into another representation. So you take psi, theta, and phi, and convert it to four numbers. So you have quaternion. And then quaternions, this is important. We have property that for 2 rotations that are very close to each other, we have 2 numbers, quaternions, which are very close to each other. And for Euler angles, we didn't have this property. We saw that if we want to have a very, very similar rotation, we must do a huge, huge jump in values. But it's possible because one rotation is described by, if it's described by quaternion q, it's also described by quaternion minus q. And why it's important? Because we had some fails in our project. That's why I tell you that. So your convert Euler to quaternion function must be aware of this fact. Otherwise, this might happen. So those frames, here you have four numbers, 4 quaternion numbers. This is one quaternion. Quaternions are normed to 1, and you have 4 indices. Anyway, here we have one number, and then here we have minus q. And this for example, and this represent almost the same rotation, but this is very far away from this one, and it's non-smooth, and neural network break, and you would like to have something like that. And then you're happy, right? Because that's easy to process for neural network and for all the other temporal machine learning algorithms. The point is, after we fix that, our model stopped producing weird glitches, and we're basically happy with models. By the way, you saw the results, and they are, I like them. Right. Then the question is, how do you model? What kind of architecture you can use for motion capture data? I would say, with this meme, that motion capture data is half computer vision, half NLP, and half sound. What do I mean by that? It's animation because it's like an ordered set of tokens, like right hand up and left leg forward and so on. You can also think about it as a computer vision, right? We are on a computer vision track, and the top results are presented on a computer vision and pattern recognition conference. And well, convolutions seem also to be natural to model this kind of data. You'll see why. But you can also think about it as a sound where you have a lot of different channels, like not one, not two, not 5.1, so like C channels, but maybe 140 or something. Next. So let me show you how you can do the convolution network on this kind of data. So you have some animation, and then you're doing the reshape, and you have this kind of tensor, and then you apply convolution. You have some latent dimension, and then you apply another convolution, and you have some latent vector, you might say, and then you do the decoding, and it basically does the opposite things, and we have the same shape. Then we can train on using some reconstruction laws and so on. But the point is, look, during the training, we can cut the whole animation into windows of like overlapping or not non-overlapping. But the point is that they will all fit nicely on GPU. We can make a batch size of, I don't know, 128, and that's fine. But during the inference, we can handle arbitrary long animations with mathematics, basically. We haven't, like, we don't have to do any like gluing, sticking, and fixing. It's all handled by convolution layers in the network. And I really encourage you to think about your problems, what might be specific in your case, where you can handle some of the problem that seems to be like very hard. Okay, so I know how to train on short animations, but will my model handle long animation? If you use correct mathematics, maybe it's possible to make it like automatically solved problem, right? This is something that I wanted to emphasize here. Okay, we are already like 20 minutes into the presentation. I feel like I might losing your attention, so let me introduce colors. And I want to share with you 4 advice. One, or maybe not, we'll go through them now. So the first advice, you must see what your model produces. So in case of like image segmentation, Neptune and AI has this really nice dashboard where you can see what your model produces. You can immediately check during the training how well my model performs, does do any weird stuff. The same with classification, the same with some text models. Those are, I think, from weights and biases. But the problem is that with animations, it's very hard to preview the animation. You just have this tensor, and then you have to somehow visualize it. So our pipeline in the beginning was to use Blender. And in Blender, you can import the animation, and it will take some time. You have to make sure that you set up this field. Here, banana will be very, very large, by the way. You import another animation. The point is that I want to compare those two BVHs. BVH is the format in which you save this tensor, more or less, along with the base skeleton. Okay, so I'm importing this, and I want to check whether those two animations are the same or more or less the same. And I don't know. Maybe they are just shifted by some like angle, or not. It's very hard to say, and it took me ages. And fortunately, Bones did develop their viewer, and now I can just drag and drop two characters, and I already see them. I see them already with some kind of a mesh applied, but maybe I want to take a look only on Bones. And well, I just have to change option to pyramids, remove meshes, and I can easily compare those animations. The point is that only when we had a proper viewer, so if you have a custom data set and custom data, only when you have a proper viewer, you can reason about your models. Before that, you can only like make some guesses, I would say. And now I can really easily compare models, and I'm happy. I can see that, oh, this model is better than that model, or at least this animation is better than this animation, because still it's hard, like, Anyway, you must make your evaluation easy. The point is that we are able to compare animations nicely, but how to compare models? And I thought in the beginning that this is super user-friendly notebook, right? I'm ML engineer. I sent this notebook to Bones, and they have some Python developers and Python animators, but nobody used this model until we really like push them for checking it. This is user-friendly, right? So you're just picking a content animation, style animation, model, and everything just works as it should. And this is the state of the viewer right now, and you can just pick 2 animations, and you can pick a model. Models are living in some REST API, and the viewer is just making requests to this API. Everything is immediately shown in the viewer. And you can see, for example, here that we're making this orange guy in the style of this purple one. And those 2 others generated guys, you'll see that they have like straight back. And this is more or less the thing that we wanted to get in this drawing. See? Straight back. Okay. So why it might be important for you, this advice? This advice might be important for you because if you have a custom domain and you need feedback from the experts, then those experts will only give you feedback if it's easy for them to evaluate models. If it's hard for them to evaluate models, they won't give you feedback. That's important. We all want to get feedback to get better models. Okay, I will not, it goes without saying that things break. And those are all the errors that we get during creating our models. There were a lot of them. Some of them make sense, some of them doesn't make sense. Sometimes you have the information, oh, you should set this setting, and sometimes you just don't know what's going on. And I would like to really encourage you to do some testing. And I know that it's very scary for ML engineers to do testing, because how to do tests, how to do like unit tests. So I encourage you to write end-to-end test. And what do I mean by that? For example, this is our pipeline. So we first have some metadata. We have to pre-process that. Then we have to pre-process animations and calculate normalizations and do the model training and maybe fine-tuning and then inference. And if you create end-to-end test for that, then you can test whether this whole pipeline, at least in a happy path, it works. So you're not doing it on the whole data set, just on like 4 animations in our case. And you're not training for like the whole epoch, even though the whole epoch on 4 animations is not that long. You're training only on 1 batch, for example. And you get something like that. So I see that, I changed something related to the data set, and maybe the training broke, even though I was changing something here or even here. And with this symbol, I see that, something's broken. I can try to fix it. And if you wonder how it may look like in your code, let's say that you have prepared BVH metadata script. So just wrap this script into a function, and you will just run this function in the script that does the pre-processing, and import this script in your testing file, and run the test. And the same then goes for pre-processing. And obviously, people that are doing software engineering, proper software engineering, and they like tests, they will scream at you, but still you'll catch some bugs, and that's good, right? We have all the things are green, and I know that when I take style ID from the CSV and not from somewhere else, the training and the inference still works, which is huge for me. And yeah, why it was important for us, we catched a lot of bugs, really, and very unexpected bugs. Bugs are usually unexpected. And we got rid of the data version versus model version mismatch. From my other projects, previous projects, I see that it was very often the case that the versions were not matching. And by the way, using frameworks like Pytorch Lightning or Hydra might really, really help you here, and it make testing much easier. Finally, what to experiment with? That's a golden question of the machine learning. What should I do next? And I would like to convince you that if you have those three advice implemented in some sense, you know that you have tools to observe. You know what to observe because you can easily check different models, and you know that if something is not working, probably it's due to the model architecture or pre-processing, and not because you took wrong normalization files. You can use common sense. And let's go through our pipeline. So we have a content animation and style animation, and we put them into the RigPlay model. Then we get some animation as a result, and then we see, is the style preservation good or bad? If it's good, then maybe I should work on a content. If not, I should work on a style. I mean, it's not rocket science, obviously. But if you're not sure whether, maybe I've used wrong normalization files, or I've used something broken in the training, maybe, I don't know. Right? If you have those implemented, it's much easier to focus on what's really, really important. And it basically removes distractions. So that's what I would like to encourage you to do. So key takeaways, if you know your mathematics, it can help you solve your ML problems. And I guess that all of you use mathematics in your projects if you're doing any projects. Yeah. And even with Agile in mind, I really encourage you to do the whole pipeline, just the proof of concept of the whole pipeline, so you know how to evaluate your models. And with that said, I would like to invite you for the last part on the future of motion capture.
Character animation. So we've got a joke about this animate button because most people out of our niche industry thinks that it's very easy to animate computer characters, and it's not. So this kind of automation would be very appreciated. But it turned out that our data set can be really improved by adding text descriptions to every action that is performed. And right now we've got 350,000 actions with the labels. And having that, we can create something like a mid-journey for character animation when you prompt and you get the movement. And now I'd like to show you the prototype of our generator that probably in the near future will change the industry for good, so that people will be able to create animations just in their environment, sitting at the table. So here's a character walking forward, but we can alter this animation with any style. So here you've got a drunk version, and all of that is generated. It's not just taken from the dataset.
And by the way, it's real time.
Yes.
So it's indeed that fast, because this data is pretty light if you think about it.
Yeah, so here's the fighting animation. We've got also some more technically useful animations like transitions from pose to pose. They can also be generated, and even something as awesome as backflip with a hero landing. Yes, so thank you very much.
We don't have much time for questions, but we would like to make some space for you to ask them, so feel free to approach us if you want to learn more about this subject, or if you want to talk about how to collaborate on it.
We'll take maybe 2-3 questions, quick questions.
this data set available for the public or not?
No, it's available commercially.
Hi, Piotr here. I wanted to ask if you were trying to do some kind of model which will predict frames between animation. For example, you have animation A and B, and you want to connect them to not look like it's glued or something.
Yes, we did. Like, yeah.
Yeah, I can say that it's one of the projects that we are also working on, but I don't think that we have to say more here. Sorry. Yeah.
And hi, you were mentioning 3 rotations, but from what I remember about the classic mechanic, you need 6 degrees of freedom to describe a movement of body.
Yeah. So what I haven't said to you is that we also have the root motion. So root is like a special joint, and that joint like goes somewhere, and you must have like XYZ position of this root, and then from this root all the bones grow in some sense, and you have this hierarchy, and then you can have rotation of each bone with respect to this one.
Okay, thanks.
Okay. Last question.
I also wanted to ask the question about the did the model learn inverse kinematics or something like this, or you implemented it yourselves?
Yeah, so we tried, and actually the results that you've seen, there were like 2 characters, like there were 4 characters, one content, one style, and 2 characters, and one was with inverse kinematics, the other one was without. And apparently from our experiments, the inverse kinematics algorithm that we had was worse than the raw version of something generated from the model. But yeah, that's also something that we probably might work on, especially not regarding foot contacts, but maybe some like objects, touching and so on. Yeah.
All right. Thank you very much, guys.
Thank you.